Deposition and erosion from glaciers. A glacier is a large mass of moving ice that forms by compacting snow by natural forces. So over here in your notes, it says, what is a glacier? So I would put this definition right here. What is a glacier? Glaciers can be found anywhere where it is cold enough to stay frozen year-round. So here in Ohio, we do not have glaciers active right now because in the summertime, it gets warm enough to melt all of our snow and ice. But in regions of the world where it's cold enough that snow and ice does not melt, so that happens in high elevations in mountains, as well as the close to the North and South Pole, where it is cold enough that the snow and ice does not melt every summer or every year, glaciers can form. Gravity is what causes glaciers to move. When enough ice builds up on a slope, the ice begins to move downhill. The steeper the slope, the faster the glacier moves. As the glacier moves, they pick up materials. These materials become embedded in the ice. As the glacier moves forward, the materials scratch and abrade the rocks and soil underneath the glacier. So these are two examples of Kelly's Island, where you can see those deep grooves and scratches and striations that have been caused by the glacier. This is an area on Kelly's Island. So you can see here the striations that occur from these grooves, these very deep gouges that have formed from the glacier. This is a video clip that's going to describe to you how glaciers form. So as you watch this video, you're going to be getting the answer for this section right here. How do glaciers form? This section right here.
Glaciers are not formed from frozen water. They are made from snow. It's only when snow turns into ice that it becomes so powerful it can change our world. On this ice cliff, you can actually see the transformation of snow into ice as it happens. Each year's snowfall creates distinct layers, many meters deep. Now above me is the fresh snow from this winter, and down here this brown line is the melt from the summer before. So as you go down through these layers, the snow gets older and older. It's kind of like the rings of a tree, with each layer being a new layer of snowfall. And it's the weight of all those snowfalls building up that starts to compress the individual snowflakes together. The further down the layers you go, the harder the snow becomes until you reach here. This is a really distinctive set of snow. It's called neve, and it formed several years ago. It's really hard. I mean, I have to dig at it with my ice axe. It's amazing stuff. It's kind of like a bubbly fiberglass. It's beautiful. And what it's telling us is that we're getting close to true ice. The more the snow is compressed, the more air is forced out of it. Removing air is what turns fluffy snow into rock-hard ice.
So one of the things I want to bring to your attention is when looking at this video, you see these darker lines in the snow, and that shows the melt. So some snow does melt, but not all of the snow melts from season to season and year to year. So as he went down into this cliff, you can see these different layers. So if I were to count these layers, this is just a rough count. I see 1, 2, 3, 4, 5, 6, maybe different layers there. So we're looking at least 6 years of snowfall. So down here, this snow could be 6, 7, or maybe more years old. So this is many different seasons of snowfall, all on top of each other. So as the layers compact on top of each other, it pushes the air out of the different layers of snow. And as the air is pushed out, the ice forms stronger and stronger, which eventually turns into glacial ice.
Really hard. I mean, I have to dig at it with my ice axe. It's amazing stuff. It's kind of like a bubbly fiberglass. It's beautiful. And what it's telling us is that we're getting close to true ice. The more the snow is compressed, the more air is forced out of it. Removing air is what turns fluffy snow into rock-hard ice. This is it. I've come down about 20 meters to the base of the cliff, and this is pure glacial ice. All the snowflake crystals in it have been squeezed down. It gives us this weird texture. I mean, it's just frozen water, but it's like solid rock. Look at that. And it's got this glassy feel to it. It's almost transparent. But now the air has gone, this ice is tough enough to take on the hardest rock.
This next video is about glaciers and how they form and the different landforms that they form.
Glaciers are also called slow-moving rivers of ice. Most common in the polar regions of the Arctic and Antarctic. Glaciers can be found in the mountains of every continent except Australia. Glaciers form in places where snow accumulates over time. It takes decades or even centuries for glaciers to form. As the snow deepens, the weight and pressure of the snow on top compresses the lower layers into ice. The weight of the glacier plus the force of gravity will gradually cause the glacier to move downhill. Most glaciers move very slowly, only about 160 feet or 50 meters per year, but some move as fast as 100 feet or 30 meters per day. Glaciers are powerful. They can carve huge chunks out of mountains as they move downhill. Because of this, they are sometimes called nature's bulldozers. Like bulldozers, they shape the land as they pass over it, but they do this in several ways. First, glaciers pick up any material lying on the ground beneath where the snow accumulates. Water beneath the glacier soaks into cracks in the rock below. As the water freezes, it forces the cracks wider and breaks off pieces of rock. This is called freeze-thaw weathering. As the glacier flows downhill, it takes these loose pieces with it. This is called erosion.
What you're watching here is time-lapse photography of a glacier. Each little blink or glitch is a month. So if you focus up here in the left, it'll kind of go through the year and the month. This is about 3 years worth of data or pictures.
Erosion. These rocks and stones scrape along the glacier bed like sandpaper, taking more rocks and stones with them. The ground beneath it becomes smooth as the glacier moves over it. This is called abrasion. The glacier transports the eroded material downhill with it. Sometimes you can see dirt and rocks in a glacier, which will give it a dirty appearance. Once the glacier flows far enough downhill that temperatures are warmer, it begins to melt. Anything that can't melt, like rocks, stones, sand, and clay, is deposited or left behind as glacial till. The ice turns into meltwater and flows farther downhill to join a lake, stream, or ocean. If a glacier reaches a body of water, the ice turns into meltwater to melt. Anything that can't melt, like rocks, stones, sand, and clay, is deposited or left behind.
One thing I want to point out here about the glacial till is notice that it's unsorted and unorganized. This is different than the deposits from a stream or river to make an alluvial fan or a delta. That's usually very organized in the fact that the larger materials don't travel as far and the smaller materials do travel very far. Here, it's very disorganized. We have large pieces at the top, large pieces at the bottom, kind of intermixed with smaller pieces. And this is very noteworthy for deposited glacial till.
Behind as glacial till. The ice turns into meltwater and flows farther downhill to join a lake, stream, or ocean. If a glacier reaches a body of water, pieces of it may break off and fall into the water, forming icebergs. Glaciers are only found in very cold parts of the earth, but during the last ice age they could be found in parts of the world that are much warmer now. Even though the ice is melted now, the landforms created by the movement of ancient glaciers can still be seen today. Glaciers can create lakes, valleys, and other landforms, and are the largest source of fresh water in the world. As they move, glaciers change the shape of the earth, making them one of the most dynamic natural features on the planet.
So as a glacier melts, it drops material that it's carrying. So it does do deposition as well as erosion. Glacial drift is the general term for all the materials carried and deposited by the glacier. So to zoom in and focus on some particular landforms, so here we have the name of the landforms, the description, which you're going to write here. Try your best to draw an image and then note whether it's erosion or deposition.
So let's start with a question. How does this giant angular boulder end up jammed in among these pine trees in Yellowstone National Park?
To find an answer, we need to learn about some of the characteristic landforms left behind as a result of glacial erosion and deposition.
A glacier is a long-lasting mass of slow-moving ice and snow. See our Classifying Glaciers video for more about the different types of glaciers.
If you do not have the definition for a glacier, this would be a good one to get if you didn't get one earlier in the video. There are different kinds of glaciers. We're not going to focus on that detail, but there are different ways to classify or different kinds of glaciers.
Just like streams, moving ice can be an agent for erosion and deposition. And just like streams, glaciers erode material from near their source, transport rock and sediment downslope, and deposit much of that material where they end.
In areas with present-day glaciers, erosion forms steep-walled, bowl-shaped depressions known as cirques at the head of valley glaciers.
Adjacent glacial valleys are typically separated by sharp, knife-edge ridges known as arêtes.
Glacial erosion can occur where ice is in contact with rocks.
Who among us hasn't frozen a large rock into a block of ice to test how tightly the ice binds to the rock? When this happens in nature, it results in one type of glacial erosion known as plucking.
Plucking happens when water invades cracks in the rock. As the water turns to ice, it binds onto the blocks of rock.
The motion of the glacier plucks the blocks of rock out of the cliff face, embedding them in the moving mass of ice and transporting them down slope.
Rocks frozen into the base and sides of the glacier act like sandpaper, scraping against the surrounding valley walls and floor, and a second process of glacial erosion known as abrasion.
Abrasion leaves behind telltale striations in the bedrock that identify the direction of the motion of the ancient glaciers.
Some striations, like these grooves worn into this limestone bedrock, can be very deep, indicating that they were formed below thick, powerful ice sheets.
So to review what we've looked at so far, so glacial grooves or striations are these scratches or gouges that were created by the rocks that are stuck inside the glacier ice as it moves down across. To back up a little further, here, these bowl-shaped depressions, these bowl areas in the mountain are known as cirques. And then the ridges are known as arêtes. Notice how it's kind of a big U valley versus a V-shaped valley. This glacier causes this change. So make sure you're recording these in your notes. Cirques, arêtes, and grooves and striations.
Combination of plucking and abrasion deepens and
Grooves worn into this limestone bedrock can be very deep, indicating that they were formed below thick, powerful ice sheets.
The combination of plucking and abrasion deepens and widens V-shaped stream valleys to produce a U-shaped profile characterized by a flat valley bottom and steep sides.
Much like this example from Scotland, and this U-shaped valley from the Beartooth Mountains in Montana.
So U-shaped valleys started as a V-shaped valley. It was eroded by a stream or a river, but then a glacier came down and carved that V-shaped valley even wider into a U-shaped valley.
If rising sea levels were to flood one of these things, we would have to call it a fjord.
Up to now, we've been focusing on processes that cause erosion. Now we want to turn our attention to features formed when glaciers deposit.
So everything we've talked about already, the glacial striations and glacial grooves are erosion. Cirques and arêtes have been created by erosion, and U-shaped valleys have been created by erosion.
Deposit material near their terminus.
Most deposits left behind by glaciers are composed of a generally unsorted mixture of clay, silt, sand, and boulders known as glacial till.
Ice at the terminus of a glacier will melt and dump piles of till. If the position of the terminus remains stationary for some time, it can leave behind a ridge of unsorted till known as moraine.
So the moraine is till that has been left behind because the glacier kind of melted in one spot for a long period of time, and it creates a ridge of that unsorted till. Those moraines can be at the end of the glacier or on the sides of the glacier.
Moraines essentially define where the glacier paused, and the position of the moraine that is farthest down the valley, the terminal moraine, indicates how far the glacier extended during its history.
Ice sheets leave behind moraines that can be traced for hundreds of kilometers across multiple states. For example, this shaded relief map of Ohio shows the positions of several moraines stretching across the northwest corner of the state and into neighboring Indiana.
So one of these moraines is actually Route 12 that goes through Finley. The reason why Route 12 is slightly raised than the other areas is because it is one of these glacial moraines, an area where the glacier paused and deposited lots of materials.
Piles of unsorted glacial till can be trapped by an advancing glacier and shaped into oblong mounds known as drumlins that narrow in the direction of glacial motion.
Behind the moraines, we also find hundreds of small lakes known as kettle lakes.
Kettle lakes form when blocks of ice break off a retreating glacier and are subsequently buried. The ice gradually melts, forming a depression in the glacial sediment known as a kettle. These low areas may then be partially filled to form a lake. Just like these kettle lakes in North Dakota. Break off a retreating
So one thing I want to point out here is this is your
glacier.
main glacier here. Your original or main glacier. Was here. This was like your original glacier. And these ice blocks, which would have been very sizable, broke off and were left behind. Glaciers melt very slowly. And so as that glacier is melting, it's washing down more sediment kind of over and on top of these ice islands that are left behind. So they're going to be completely covered by sediments and material, but they're still ice. They're still holding that space.
Subsequently buried. The ice
As time moves on, that ice will eventually melt. And when it melts, the water is going to flow away, and we're going to get a sinkhole effect from that missing ice that was there. And so the sediment is going to depress, and you're going to get these depressions. You're going to get these holes. And these are fairly large, the size of lakes, the size of ponds. These are very, very large.
Sediment known as a kettle. These low areas may then be partially filled to form a lake. Just like these kettle lakes in North Dakota.
A feature known as an esker may be formed when till is sorted by streams flowing at the base of the melting glacier.
The sediment deposited within these subglacial streams leaves behind a skinny, sinuous landform.
Likewise, as the glacier melts and its ice turns to water, meltwater streams transport sediment away, depositing some of it in the adjacent outwash plain.
So those outwash plains are very similar to deltas or alluvial fans.
Thick ice sheets can pick up very large rocks, known as erratics, from one location and deposit them elsewhere, sometimes hundreds of kilometers from their source. By matching the geology of the erratic with their source area, we can unravel the direction and distance of motion of the ice that move these wandering boulders.
So this boulder looks like if somebody were to come and hit it too hard, it could tip over and roll away. That's not the case. The glacier kind of dropped it in this position, and there it has stayed. And even if somebody were to come push on it as hard as they could, or run a car into it, or kind of push it with a tractor, it would maintain its position. It's pretty stuck there. These are known as glacial erratics. They are an example of deposition.
And that brings us back to our 500-ton friend among the trees in Yellowstone National Park. This boulder of metamorphic gneiss sits on top of volcanic rocks, hundreds of millions of years younger in age. And the boulder must have been carried at least 25 kilometers from its source.
Let's finish off with a matching exercise. We will show you pictures of 4 glacial features. Match each one with a term from the provided list. We'll check your answers when you're done.
So, how did you do? The 2 learning objectives for today's lesson. How confident are you that you could do these things?
This is a better view of those glacial grooves on Kelly's Island. It's an area that at one point in time was mined, and this particular area has been preserved so that people can see it. So this is looking at a V-shaped valley. Then the glacier comes through, and we're left with a U-shaped valley.
We're on Penyvan, in the heart of the Brecon Beacons National Park.
Like most of Wales, 23,000 years ago, the valleys of the Brecon Beacons were filled with ice. Massive glaciers that completely dominated this landscape. Over the next 12,000 years, the glaciers came and went as global temperature increased, and the last glaciers were still here just 11,000 years ago.
We only have to look around to see the marks that these glaciers have left on the landscape. Look at this magnificent valley. It's not a V-shaped valley created by a river cutting down into the landscape, but it's a U-shaped valley that's been carved out by a glacier.
With a little help from his freezer, Tim has been trying to better understand how glaciers have shaped this landscape.
So to understand how glaciers turn V-shaped valleys into U-shaped valleys, we need to do a little bit of kitchen geography. So the first thing that we need is a bottle of water, and we're going to put this in the freezer. Then we need another bottle of water, but in this bottle of water, we're going to put some rocks. We're going to shape these rocks so they're just lying along the bottom of the bottle, and we're going to put that flat into the freezer. Now we're going to wait. After a few hours, we're going to cut away the plastic. This is what we've got. 2 model glaciers. One with no rocks at the bottom, and one with rocks at the bottom. So we've got 2 halves of a watermelon here, and we're going to use these to show the importance of glacial abrasion. If I take the glacier with no rocks at the bottom, you can see I could be rubbing this over the watermelon for days on end, and nothing's going to happen to the skin of this at all. Whereas if we take the one with the rocks at the bottom, let's see what happens. So if we rub this over here, we can see the contrast is massive. The glacier with the rocks at the bottom of it has scoured away the skin of the watermelon, and this is very similar to a real glacier. Now, as the glacier moves down the hill due to the force of gravity, it picks up or plucks material from the valley bottom. This material is then attached to the glacier, and in a process called abrasion, it scours away the landscape. The rocks literally act like sandpaper. So we've got another watermelon here, and into the watermelon we've cut a V-shaped valley, just like we would get from a river. But what we're going to do is see what happens and how that valley changes when we send a glacier down. So, If we take our glacier away, we can see how those processes of flocking and abrasion over thousands of years have eroded the valley sides and the base of the valley to turn that V-shaped valley formed by a river into a U-shaped valley or glacial trough.
And here back in the field, we can see this glacial trough. Along the valley sides are spurs or hills, which would have once reached right into the centre of the valley. These have been chopped off or truncated by the glacier moving down the valley. We call these truncated spurs.
And that is kitchen geography. So after a few hours, we'll take our...
So a lot of that went very fast in those videos, but I feel like those videos do a nice job of showing you some nice images and explaining it. So I'm going to circle back and go over a couple more things. So here's an example of an erratic. Glacial erratics are rocks moved by glaciers that now rest on bedrock composed of different material. This is an example of a glacial erratic in Acadia National Park in Maine, known as bubble rock, and there are others known as balanced rock. So even though that guy is pushing on that rock with all of his might, it's not going to fall off that big cliff. And if you ever get the opportunity to travel to Maine and go to Acadia National Park, I highly recommend it. So glacial erratics are deposition. Here are glacial striations or glacial grooves. As glacials reach their maximum size, they are scoured by the topsoil and the bedrock with their load of debris. In areas where the glacials are carrying large amounts of clay and silt, the glaciers act like sandpaper and they polish and smooth the bedrock, and they can cause scratches and grooves to form as well. So here's examples of glacial striations, and the Kelly's Island example shows that even more exaggerated. We call those glacial grooves. Here you have an example of a moraine. So when a glacier gets to the point where they can melt, so either they've moved down south enough that they've reached warmer temperatures, or the climate around them has warmed up, the glacier is going to melt. When large amounts of rocks and sediment are deposited by the glacier, sometimes these rocks pile up at the end of the melting glacier, and this is called a moraine. These moraines can be large enough to block U-shaped valleys and create lakes. They can create ridges and small hills. So this is an example of a terminal moraine right through here that kind of cuts through this U-shaped valley. So here you kind of have a U-shaped valley, but a moraine has formed through that U-shaped valley here, cutting that valley off. And so in turn, we get this lake that forms. This is also located in Acadia National Park. Here's an example of a kettle lake. The example of those blocks of ice being left behind and then melting much later after sediments have been piled on top of them. When they do melt, they leave a depression behind, which can eventually form a lake. Here's an example of a drumlin. Going back to our time for geography example to explain these drumlins to you.
One of the most exciting things about physical geography is that it can help reveal some of the hidden secrets of our planets. And landscapes like this are full of hidden secrets, but they're easy to miss if we're not looking for them.
We're here in Teesdale, in North Yorkshire, and on this wintry day, a great mystery lies hidden right beneath our feet. In the midst of this broad U-shaped valley, we have this hill about 20 metres high.
But why is it here? What could possibly have created this landform? Let's go and see if we can find some hidden clues. The first clue is in the shape of the hill. If we look at the side facing up the valley, we can see that it is steeply sloping. But on the side facing down the valley, the slope is much gentler. It almost looks like an egg that's been half buried in the ground.
The second clue comes in the shape of the valley overall. Rather than having a narrow V-shaped valley carved by a river, which is common in upland environments, what we have here is this big, broad U-shaped valley. And what this tells us is that this valley has been carved by ice. And as recently as 14 or 15,000 years ago, this valley would have been filled with ice. It would have been flowing down the valley.
So what do we know about glaciers? Glaciers form in very cold environments where snow piles up over time and becomes compressed into ice. That ice then slowly flows down slope and it carves away at the valley floor through abrasion and plucking. But the base of the glacier also sculpts and molds big piles of sediment as it flows down the valley, just like the ripple on the bed of a river.
This is what the sediment at the base of a glacier looks like. You can see here we have this sediment which is made up of a mixture of fine sediment particles, of these small pebbles, and of these large boulders. And this chaotic jumble of material is known as glacial till. As the ice melts at the base of the glacier, it saturates the sediment and makes it easy for it to be molded and shaped by the force of the glacier flowing over the top of it. So we call this process subglacial sediment deformation. So sub, like submarine, which will be under the water, here subglacial means under the glacier. So subglacial sediment deformation refers to the molding or deformation of sediment underneath the glacier. Now if we look closely at one of the boulders that we've taken out of this glacial till, we can find one final clue that shows us that the sediment has been deposited underneath the glacier. If we look closely on the surface of the boulder, we can find it's covered in these scratches or these striations. And these would have been created as the boulders within this till ground over each other as the till was molded and sculpted underneath the moving glacier.
So this is some glacial till, and it's saturated with water, just like we'd find at the base of a glacier where the ice is melting. The glacier will be flowing over the top of this glacial till. Now, as the glacier flows down the valley, sometimes it comes into contact with a stiffer, sticky, heavier piece of sediment on the valley floor. When that happens, all the sediment bunches up. The ice flows over the top of it and then continues down the valley, creating this hill with a steep side facing up the valley and a smoother, streamlined side facing down the valley where the ice continued to flow away. From all these clues, the landscape has revealed to us the secret of how this hill was formed. It was created by a glacier flowing over the ground, moulding and sculpting the sediment underneath it in a process that we call subglacial sediment deformation. And we call these landforms drumlins. The length of drumlins can range from about 50 metres to several kilometres long, and their height ranges from a few metres tall to up to 100 metres tall, or 5 times as big as this drumlin here behind me.
Here at Holwick, this drumlin looks like it just occurs on its own. But in reality, this drumlin forms part of a much larger group of drumlins that covers the whole of the valley floor. The physical landscapes of our planet are shaped by different processes. Now, although this drumlin was created by subglacial sediment deformation, this may not be the only process that can create drumlins. When a glacier melts quickly, this can result in huge amounts of water flowing beneath the glacier. This happens during hot volcanic eruptions when lava melts the ice, or when water becomes trapped beneath the glacier and the ice dam bursts. This can create a subglacial megaflood, or Jökulhlaup, generating powerful flows of water that flow under the ice to erode the sediment and to create the drumlins. So drumlins can form both through deposition and through erosion. Deposition associated with subglacial sediment deformation, and erosion associated with catastrophic meltwater floods occurring underneath the ice. Like topics right across geography, the formation of drumlins is still a subject of continuing research. The main theory at the moment is that drumlins are formed by subglacial sediment deformation, the moulding and sculpting of sediments beneath the glacier by the force of the flowing ice. Alternatively, some drumlins could be eroded by flowing meltwater underneath glaciers, or perhaps they could be formed by a combination of the two processes working together.
So I would note there that drumlins, depending on the
People
process,
should study geography because there's no more relevant subject. Kingston University is
the process of both erosion and deposition. Erosion and deposition, depending upon the process. So that brings us to the end of our gravity notes. So through the different pictures and the different videos, hopefully you were able to describe and draw and note erosion or deposition of each one of these landforms. Feel free to rewind and get any of the ones that you may have missed. Thank you so much. Have a great day.